No, it was the advanced attitude control. Have like power optimal solution, but as you converge to zero, a matrix you have to intersect is singular. So it converges and then bounces out as it like becomes numerically stable. So it's not a very good solution. I mean, what I can do is as soon as the what is that? Like the ratio of eigenvalues. I forget what that's called. The one that tells you how singular your matrix is. Like when MATLAB is like condition number, when the condition number of the matrix gets too high, you can just switch to an alternate solution, but you don't get a lot of benefit. Questions?
Okay, so I think we're ready to pick up from where we left off on last Thursday. Hope everyone had a good Labor Day weekend. So we're going over sort of basic orbit transfers and orbit optimality. And when we left off last time, we had introduced, first of all, last time we introduced the Hohmann transfer. Then we talked about two other ways that sometimes can save fuel with respect to doing a Hohmann transfer between two circular orbits. One is the Bielliptic transfer, and here we sort of boost the orbit up to a larger radius. Then we, this way. To a larger radius beyond the target radius R2. We do another boost maneuver to raise periapsis, and when we get there, we then are going faster than local circular, so we slow down to capture into R2. And sort of a limiting case of that is the parabolic transfer, where we actually just boost to escape. When we get far enough away, the cost is essentially zero to do this periapsis raise maneuver. And then we come back on another parabola, and then we're going faster than local circular, so we slow down, and then we get transferred into the second orbit. And we're sort of looking at this. Comparisons between these, and we had first off come up with the limit at which the parabolic transfer is always fuel optimal over the Hohmann transfer, and that was at about 11.9 radii in terms of the ratio of the two orbit radii. And then we had started looking at the Bielliptic transfer, which is a lot messier. It's got two parameters, the ratio of the target orbit over the initial orbit, and then the ratio of that larger orbit, R3, over the initial orbit. We call those script R and script L. And we had just shown that what we would hope for the Bielliptic formula, if we make L equal to R, it actually is equal to the Hohmann transfer. What we'd like to find out is when is the Bielliptic transfer actually cost less than the Hohmann transfer. And the way we had posed this right before we left off was if we're just at a value of R, and if we increase this L to be R plus some very small epsilon, when is this sort of a transfer optimal? So here we're in a circular orbit, and we're just wondering how big does that circular orbit have to be such that if we just do a very small boost trajectory to raise the apoapsis up a value epsilon, or the way I pose it here, r epsilon, and then come back down and then circularize at a slightly higher, or at a larger orbit, when is this guy actually optimal over the Hohmann transfer? Okay. And essentially, we're asking the question, when is JH minus J by, when L is equal to R times 1 plus epsilon greater than or equal to 0 for epsilon greater than or equal to 0? Now, to answer this, well, the math gets kind of messy. So first of all, it'll be a homework, and I'll probably assign the homework by next time. Well, what I'm asking is just when does this happen for some epsilon, and in fact, we could try to answer it for epsilon being much less than 1. That may actually be a little bit easier, because then we can actually do like a Taylor series expansion of this bielliptic cost. If you look at this, replace here L everywhere with R times 1 plus epsilon, you can imagine doing at least a first order expansion of that guy. So if we have that sort of a perspective, and if we assume epsilon is much less than 1, the question changes a little bit, and it becomes, when is JH tilde as a function of R minus, I'll just restate it again, epsilon greater than or equal to 0, and if epsilon is much less than 1, we can expand this guy in a Taylor series expansion. So this becomes JH tilde R minus, first order, epsilon equals 0, this just becomes J bielliptic of R. Next order becomes partial of J bielliptic with respect to epsilon evaluated at epsilon equal to 0 times epsilon, and then minus terms of order epsilon squared. And we want to know, when is this guy greater than or equal to 0? But I've already stated, and you can show, that this bielliptic, when we have the R or the L equal to R, meaning that you actually don't do this third maneuver, this guy is just equal to the Hohmann transfer. So these two guys actually cross out. We're going to ignore higher order terms, so we just focus in on this first order term. So this is going to happen when epsilon is positive but small. So it's going to happen when negative of, the partial of this bielliptic function with respect to epsilon evaluated at epsilon equal to 0, when this guy is greater than or equal to 0. Okay. So this is something that you could actually check. And here I actually do check it. Got like a page and a half of algebra, which I'll spare you. But if you go through the math, and this will be another homework problem, what you can reduce this condition to, and all we're doing here is, and I guess at the least I can restate this. So we write this as R times 1 plus epsilon. This guy becomes equal to
Professor?
Yeah?
Shouldn't it be dJBI over derivative with respect to R instead of epsilon?
No, because I'm actually just doing the expansion in terms of epsilon.
Okay.
So it doesn't matter what my small parameter is. I don't have to do R epsilon. Although to actually carry this out, you would use some sort of, you could use a chain rule, but it's take the partial of J by with respect to this guy, which would be like L, then take the partial of L with respect to epsilon. So you could do that, although you don't have to. Functionally, once I just write it like this, that will really expose epsilon, and I could just directly take the partials of that. Everything else will work out okay. Okay, so this guy, if we make the substitution, falls into the following form. Square root 2 script r 1 plus epsilon over, this would be, yeah, I was right, r 1 plus epsilon plus 1 minus 1 plus square root 2 divided by, I've got a 2r over r squared. Those cancel, but we'll just leave them in here for a second. 1 plus epsilon times 2 plus epsilon minus square root 2 over r times 1 plus epsilon times r times 1 plus epsilon, close, plus 1, close the square root, plus square root 2r times 1 plus epsilon over r squared times 2 plus epsilon minus 1 over square root of r. Okay, you can check this out at home. There should be some simplifications. This guy and this guy should cancel. This guy and this guy should cancel. But yeah, once you write it like this, you can just take the partial with respect to epsilon to do that expansion. Okay, anyway, if we do this, what we end up with, so after some algebra, we end up with the following polynomial, r cubed minus 15, r squared minus 9r minus 1 should be greater than or equal to 0 for that to hold true. There's only one root that we're interested in here that's greater than 1, and that becomes r is equal to 15.5817, etc. is the root that we're interested in. And so what this means is that for r greater than 15.5817, so if the ratio of the final circular orbit to the initial circular orbit is greater than 15.58, etc., any bielliptic transfer is indeed optimal over the Hohmann transfer. So because at this point, even a arbitrarily small additional boost of that upper, of that transfer orbit saves you a little bit of fuel. So we have to note at this point, especially for epsilon very small, close to 0, we still note that the hyperbolic cost is still less than the Hohmann cost at this value of r. Because here the transition actually occurred at r equals 11.9, etc. And in fact, it turns out that this bielliptic approach that we've just derived is actually valid for larger and smaller values of radii, but it turns out it never actually beats the parabolic cost. And we'll actually talk a little bit about that, because it has some, it doesn't have any real implications, but it's an interesting demonstration of how optimization works in some points. Okay. So a couple things to note here. For any r greater than approximately 15.6, any L greater than R will reduce cost. For 11.94 less than R less than 15.6, there exists, and sometimes I use backwards E, it's mathematical for there exists, a distance, I'll call it L sub R, backwards epsilon, such that, it just shortens things sometimes, such that the bielliptic cost at R and for L greater than or equal to this L sub R is less than the Hohmann cost. So in fact, even if we're less than this 15.6, turns out that there can be bielliptic transfers that actually cost less than the Hohmann transfer, but they're not an epsilon away from the Hohmann transfer. You have to actually boost it up to a higher value. And I actually have like a simple GNU plot of this. Load. Okay, so what this is showing is the Hohmann cost minus the bielliptic cost. And we have three things we want to plot, so it gets difficult. We want to plot the difference of that cost, see when it's positive, when it's negative. When this cost is positive, the bielliptic is cheaper. When it's negative, I'm not plotting those. That's when the Hohmann is cheaper. And what I'm plotting, and then the other two variables are R, the ratio of those two orbits. That's along the x-axis. And then L. So L is this additional guy that we boost up. And since that's the third parameter, and I don't want to try to show a three-dimensional plot, what I do is I plot different values of L. First I make L equal to X, and that should actually just make a zero line. It doesn't even show, because that's just the Hohmann cost. L equals X, or really this value of R, plus 0.01, plus 0.1, plus 1, to just probe the effect of boosting it to higher and higher orbit radii. And what we see is that actually this cost, or the transition cost, actually does come down to lower and lower values. Now, let me do a couple things with this. First I'm going to replot this guy at one slightly higher value, x plus 10. Okay, so now I boosted it up, x plus 1 and x plus 10, and we see, yeah, boosting up to a higher value of that transition radius gives us optimality before boosting up to a lower value of 1. We don't even see that green guy anymore. And let me get rid of the there. And here, if I make this just a linear scale, look a little more closely, what we see is that this, when I boost to a higher and higher value in terms of L, I'm getting closer and closer to parabolic, and we see that point of transition gets smaller and smaller. So here it's at 14.3 radii ratios. Up here, this guy, where I'm just adding 0.1, is at seemingly 16. Yeah, I don't think I have good enough resolution in this. It should be around the 15 value. And if I boost it up one more time, we plot it J plus 100. You see this guy comes in even closer, and it gets closer to the 11.9 value, which is actually where the optimality transitions for the parabolic cost. One thing to note is as I boost to a higher and higher value, this positive number, and this is how much you save over the Hohmann transfer, always dominates over the guys that I've boosted up to a lower and lower value. So, in fact, what this is telling me is as I go to a higher and higher value of L, I'm always saving more and more and more fuel. And what this really means is that the bielliptic transfer is actually never optimal as compared to the parabolic transfer. And I'll come back to that in just a minute. I want to point out a couple more things. Because these won't be true in a few minutes. So far, in the theory we've been doing, all of our transfers are symmetric. Meaning the cost for R1 less than R2 is equal to the cost for R2 less than R1. We just switch these guys around. The cost is going to be exactly the same. We just assume this for convenience. What this means is that we can start to draw what we could call an optimality chart, which is going to show us as a function of what value we use, as a function of what the value of R is, what the optimal transfer will be for our given problem. Let me quantify this. So for this Hohmann transfer problem, going from one circular orbit to another circular orbit, the way we've defined it so far, in terms of the initial problem that's specified by R, and this goes from 1 off to infinity. For a bielliptic transfer, it's quantified by L. This goes from 1 off to infinity. And then we have the parabolic transfer that actually occurs when L is equal to infinity. And we can sort of assume that we can cap the sky at infinity. What we would show in the optimality chart is where are different sorts of transfers optimal. And this guy is actually pretty easy. We know that when we get to R equals 11.94, everything to the right of this is the parabolic, I'll just write J sub P, to show that the parabolic cost is actually optimal. Below this value, we know J sub H is optimal, so it's the standard Hohmann transfer is optimal. And what we found with this bielliptic is that there is this sort of interesting transitional regime that goes from 15.6 and below. It goes up there like this. And what this shows is if we don't want to do the parabolic transfer, but instead just want to do the bielliptic transfer, where it's optimal is actually a slightly smaller domain, and it ranges from 15.6, and in fact, larger than 15.6, any bielliptic transfer is going to be cheaper than a Hohmann transfer. And in fact, as you go to a larger and larger L, it's always going to cost less and less and less. So you sort of choose what's practical for yourself in terms of that boost L parameter. But then between 11.94 and 15.6, depending on what limit you want to place on your L transfer, what is going to be optimal in terms of the Hohmann transfer and what's going to be optimal in terms of the Bielliptic transfer is actually going to change. However, if we want to talk about real optimality, independent of what's practical or not, what is the real minimum cost function, we just don't consider this Bielliptic transfer. And in fact, this region here has some theoretical interest, but it has no practical interest in terms of the answer to our problem. So there we have this very simple demarcation between optimality, the Hohmann transfer to the left, and the parabolic transfer to the right of this 11.94 line. So this is combining this optimality chart in one place in terms of R and L. It turns out, however, we don't actually need this L because it doesn't play a role in the optimality. So what we actually can do, which will turn out to be a little more useful in a bit, is to break down our optimality chart, not in terms of the ratio of R1 to R2, but as a function of R1 and R2. And we have this directionality in here because it's going to become important in a moment. So first of all, we can draw the line R1 equals R2. This is the line script R is equal to 1. And this goes from 1 to infinity, 1 to infinity. And what we know is that R2 equal to 1, R1 equal to 11.9, dot, 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 dot. The Bielliptic transfer starts to become optimal. And similarly, which is actually what we were doing before, R2 is equal to 11.9, dot, dot, dot. And this, the ratio of this guy over R1 becomes optimal at this point, and this guy goes off like this. So then in this diagram, in this region here, parabolic is optimal. In this region here, parabolic is optimal. In this intermediate region here, we have that the Hohmann transfer is king and is, in fact, the optimal transfer. So I'll call this the optimality chart because it gives us a graphic representation of what is optimal as a function of what our mission goals are or what our transfers are. Okay. I'm going to put in one aside. Well, I'll put in some observations. And let me change this to global optima. So we go back to this chart. If you think about the Hohmann transfer, almost everywhere except when we get up to this special point at 15 point whatever, and then from here on out, it is different in a way that I'll talk about in a moment. Everywhere else in this diagram, including these regions where the parabolic transfer is actually optimal, you really have no idea that these other optimality points exist with respect to the Hohmann transfer and looking at all transfers locally close to the Hohmann transfer. In fact, if you think about it, the Hohmann transfer is quite simple, and if you just restrict yourself to these two impulses, and at every point you just say, well, for this impulse, if I make it a little bit larger, a little bit smaller, if I wiggle it this way or that way, am I going to save any money or any fuel or propellant? The answer is no. It's always locally an optimal transfer. Okay? There's nothing that you would ever sensically do differently if you were flying your spacecraft around, just based on what you see in the neighboring cost function of your transfer space, other than a Hohmann transfer. In fact, that's probably even true even when you're up here, where you know that even if you do an epsilon bielliptic transfer, that's actually going to save you money over the Hohmann transfer. Because that's a very different set of procedures. Instead of doing this two impulse transfer, you're actually changing the whole problem and changing it into a three impulse problem. Okay, so it's a fundamental change to the whole, if you will, topology of this transfer sequence that you're exploring. So if you're in a position where R1 over R2 is greater than 11.9, you may still be doing a Hohmann transfer and sort of be happy as a clam because you don't realize that there's another better way of doing it. And in fact, you can save, depending on the ratios, a considerable amount of propellant by pursuing one of these other approaches. But essentially, you'll never know it just by looking in your neighborhood. So that's what I mean by this. Global optima are not necessarily close to the local optima. And in fact, if someone hadn't had the bright idea of checking to see if a parabolic transfer would save you fuel over a Hohmann transfer, I don't think you could come to that conclusion necessarily just looking at the space of Hohmann transfers. The clearest pathway to that would be that, first of all, for some reason, you'd have to start investigating the space of not just Hohmann transfers, but bielliptic transfers, boosting up a little bit and coming back down. Realize that once you get beyond 15.58, that, oh, this guy actually starts to save you a little bit of fuel. And then you would, studying that problem, realize that actually, once you're beyond this point, any addition of fuel, actually, any addition of that boosting radius saves you fuel. And from that process, sort of go off for L going to infinity and then end up at the parabolic cost transfer. Okay. So that's just pointing out for this very simple problem that what's really optimal is in some sense not even close in terms of operations to what you would think is locally optimal. It's a little interesting why this happens like this in this particular case. And while it's kind of hard to draw, you can sort of show a plot of the cost of the bielliptic transfer as a function of this parameter L. And you could look at different values of R here. And essentially, this is really a heuristic plot. If you have a situation where R is less than 11 point whatever, this cost function actually goes up like this. And the larger and larger you make L, up to infinity, the more and more it costs. When you're actually at R equals L, this curve actually has this little maxima. And then in the limit, it goes off, and it's equal to a Hohmann transfer, if this is equals 1. But the bielliptic transfer, going to a larger value of, this curve is 11 equals 11.9, whatever. The bielliptic transfer still looks like it costs more money. Okay? And then as you go to a higher and higher value of R, even though you can in this case, it goes off to, you have to go off to infinity to save money. If you go a little bit larger, you will have this little maxima, but then it will come down and go off to infinity. And eventually, if you get up to that 15.6 value, this guy's actually stationary, and then it drops off to the limit as L goes to infinity to the lowest cost. And if you go to, this would be R equals 15 point whatever, and if you go up to R greater than this, this is then always just a negative slope on your J bielliptic. As you increase L, you'll always save more and more fuel. So this is actually a pretty complicated function, although we can certainly understand it in all cases. So this previous statement, though, about global optima not necessarily close to local optima, at some level it's a little discouraging, because it sort of means, you know, if you're studying a certain class of transfer, there really are no guarantees that looking at small variations of these transfers is ever going to give you a better answer. Even if it gives you a slightly better answer, for all you know, there might be this really killer transfer out there that you just haven't thought of yet that could save you a lot more propellant or a lot more fuel. So in one sense, it could be a little discouraging, but in another sense, it's a little bit exciting because it fosters, if you will, creative thinking. And in some sense, it motivates you to think outside the box. In general, that is true for optimization, optimal control, and the like across the board. Now, unfortunately, people have sort of beaten the two-body transfer problem to death. But you never know. There might be some other clever ideas out there that people haven't come upon yet or figured out yet. One of them that has been figured out, but much after the whole Hohmann transfer theory was developed, and even the bielliptic and parabolic transfer theory was developed, is a class of transfers called aero-assists. And here, the idea is actually simple, and at some level, it's not fair because you're actually using your environment to save fuel. You're not just relying on gravity and propellant. But really, nothing is fair in orbit mechanics, right? Or on Love and War or whatever. And so here, you're doing the use of drag forces to effect orbit transfers. Now, this only applies for cases where R1 is greater than R2, when you want to go from a higher orbit down to a lower orbit. The other case just doesn't work because you're using a dissipative force. You're going to actually be throwing away energy, not by using propellant, but by using drag. So the only thing you'll really be able to do with this sort of an approach is to shrink your orbit. You're not going to be able to do atmospheric flybys and expand your orbit. That would violate a lot of different rules. What we also have to do is we have to bring another scale into the problem and assume a planetary radius r, which is really then the atmosphere height. And really, you have to also assume that there's an atmosphere. So this sort of an approach works really well at Earth, at Mars, at Venus. It works in principle at Jupiter. Doesn't work at the Moon. Doesn't work at a small airless asteroid. Probably wouldn't work very well at Vesta or Ceres, even though they may have a very tenuous atmosphere, because it would potentially take you forever to actually dissipate energy using this approach. So the idea is actually pretty simple. But that optimality chart that I showed before changes completely once you take this into the mix. Because as soon as you have some sort of a transfer that actually saves you propellant over a different sort of a transfer, it's sort of a, unless it turns out to be extremely complex, like the parabolic transfer, which just takes, too long, or the parabolic transfer. It's sort of a no-brainer that you always try to do that sort of a transfer, because propellant is money or propellant is science. Because for every kilogram of propellant that you put on board of a spacecraft or a satellite, that's 1 kilogram of, well, the ratio is probably different, but effectively it's 1 kilogram of science instrument that you can't put on there. Okay, so you limit yourself. So you always want to cut propellant. So here's the situation. We have 2 radii, R1 and R2. So now we have R1 greater than R2. I guess this is what we had before. And the idea is pretty straightforward. You're in a circular velocity here. You do your delta V1 to actually change your energy. But now you actually do it such that you come down and you graze the surface of the upper atmosphere, you graze the upper atmosphere. Now you want to be a little careful because you don't want to go too deep into the atmosphere because you'll burn up because you're going at orbital speeds, many, many kilometers per second. But the atmosphere decays exponentially. So there's always going to be some height where you will dissipate some energy, but not so much that you'll torque your solar arrays off or you'll heat your spacecraft up to the point where things start to go bad. Okay, that point exists for every body since nobody's atmosphere goes off into the whole of space. So you find this, and we just, in a dynamic sense, we just say that, well, that altitude is R. Okay, that's where the scale height or the height of the atmosphere is. That's where you can start to generate some energy loss. In general, you don't do this at once, but you do this many times. Every time you go through that periapsis, you lose a little bit of energy. And if you go through the orbit mechanics, what happens is the position where you're at is actually conserved. The periapsis is conserved. Okay, what changes is your speed at that periapsis. And what that does is it pulls down your apoapsis radius. So every time you go through this upper atmosphere, you actually lose a little bit of energy, and when you come back up, your apoapsis is a little bit lower. And you repeat this process, and this is a control variable. You can try to do it in fewer, larger steps. You have to go deeper into the atmosphere. You can do it in many, many, many small steps. You would be just at the limit of the sensical atmosphere. And you do this until apoapsis comes down to radius R2. When you're there, then you're actually at apoapsis of this transfer ellipse that would keep on happily decaying until the thing became circular and then spiraled in. But you want to stop the process here, so then you do a boost, your delta V2, to put yourself back onto the circular orbit at a radius of R2. So this is essentially what an aero-assisted transfer is. And we can come up with a pretty simple statement of it. Delta V1 is just going to be local circular mu over R1 minus the apoapsis speed of this ellipse with periapsis at R. So that becomes 2 mu R1 plus cap R over R1. Delta V2 is just a similar maneuver, square root mu over R2, except now you're boosting back up to circular. I write it like this just so that it's always positive. Square root 2 mu R2 plus cap R over R2. And we add these guys together, and we come up with what I'll call delta V aero-assist elliptic, AE, and, well, it's just the sum of these guys. As you can imagine, there's also a, well, you could imagine that there could be a parabolic option to this guy too. And if you had imagined that, you would indeed be correct. And this guy is a little crazy. But again, let's say we have our radius R1, radius R2. We now have our planet at the center with an atmosphere. 1, R2. And what you do here, instead of taking speed out to drop your periapsis, make sure I drew that right. Yeah. You now boost speed to go off into a parabolic orbit. You get very far away, but when you're very far away, you can do the same trick that we did with the Bielliptic, and then you can actually change your, do a very small maneuver to drop your periapsis down to the radius r of the planet. You come back in on your parabolic orbit, you graze through the atmosphere there. You're on a parabolic orbit, so as soon as you graze through the atmosphere, you lose just a little bit of energy. Suddenly you're in an elliptic orbit, but a very, very high elliptic orbit. Okay? So now, even though this first maneuver takes an infinite period of time, the second one only takes slightly less, okay? And you go all the way off, but now you're in a captured elliptic orbit, so you come back down. Every time you skim through the atmosphere, and at some point you actually pass through the original orbit that you started on, okay? Keep on going down, and finally you get to this guy here where your apoapsis is at R2, periapsis is at R, and then here you then boost your orbit with delta V2 to get back onto your circular orbit. So this one is interesting because you do two maneuvers, both of them increase your energy, yet the net effect is to actually lower your energy, or well, to actually, yeah, to come down to a tighter, smaller orbit. So here, the cost, delta V1, is square root mu over R1 times root 2 minus 1, just the cost to escape from a circular orbit. Delta V2 is root mu over R2, it looks like the other one, minus square root 2 mu cap R plus R2 cap R over R2. And then Aero-assist parabolic, if we add these two guys together, we then get square root mu over R1, root 2 minus 1, plus root mu over R2, minus root 2 mu cap R over R2 plus cap R times R2. Okay, so with this cost and the previous cost, and just for the notes, let me just write this guy out. Just add it up here. We note that we not only have our mu value in our R1 and R2, but we have this new parameter, which is actually the radius of the planet. And that actually plays an important role in deciding what's optimal and when it's optimal. what we'd like to do, similar to what we did before, so if you will, these guys are now a function of R1, R2, cap R, and mu. Same thing with delta V, aero-assist parabolic, R1, R2, cap R, and mu. And we'd like to normalize. And a little bit different than what we did for the Hohmann and Bielliptic and parabolic transfer. Here we actually normalize these guys by square root of mu over cap R, which is local circular velocity at the top of the atmosphere. It just turns out that that's what makes this whole, these expressions easier. And it gives us, replaces R1 and R2, if we do that, with two new parameters, which, for whatever reason, we call alpha. Alpha 1 is R1 over cap R, and alpha 2 is R2 over cap R. So we go through, do this normalization, and we then have our cost functions for the aero-assist options. And I'll write these out in detail. So the first one is for the, if you will, the elliptic aero-assist option as a function of alpha 1 and alpha 2. After normalization, this is 1 over square root alpha 1 minus root 2 alpha 1 over, or 1 plus alpha 1 plus 1 over root alpha 2 minus root 2 alpha 2, 1 plus alpha 2. So very symmetric in alpha 1 and in alpha 2. The parabolic cost is equal to 1 over root alpha 1, root 2 minus 1, plus 1 over root alpha 2 minus the same guy, 2 over alpha 2, 1 plus alpha 2, close this. And really what we need to compare this guy to is the Hohmann transfer, and then eventually to the parabolic transfer. But let's just rewrite this in terms of the Hohmann transfer. If we normalize this by square root of mu over cap R, we also then rewrite the Hohmann transfer in a slightly different way, scaled by this additional parameter. And that now becomes 1 over root alpha 1 minus square root 2 alpha 2 over alpha 1 plus alpha 2 alpha 1 plus root 2 alpha 1 over alpha 1 plus alpha 2 alpha 2 minus 1 over root alpha 2. And we just note that alpha 1 over alpha 2 is just our old parameter, script R. And here we always assume this is, again, greater than 1. Okay. So what we really want to do is we want to understand the optimality chart for aero-assisted transfers in terms of really just these two parameters, alpha 1 and alpha 2, which are very similar to that previous optimality chart that had R1 and R2. Divide both of those by the radius of the planet that you're at. So we have three cost functions, and we want to compare each of them with respect to every other one. So for here, we actually have three different inequalities that we want to understand. Okay. First of all, we can say we want to know when is JH of alpha 1, alpha 2 less than or equal to JAE of alpha 1 and alpha 2, or vice versa. What we really want to understand is when are these two guys equal to each other, because that's going to be the boundary between when Hohmann transfer is optimal or when an aero-assist is optimal. We can also look at Hohmann cost less than or equal to j sub p, alpha 1, alpha 2, or vice versa. And finally, we also should compare these two guys with respect to each other. To find out, is there a region where the one sort of aero-assist transfer dominates over the other sort of aero-assist transfer? And to make our life easier, to some extent, we just define 3 new functions, and in this case, study their zeros. So sort of an arbitrary notation, what I'll call G sub 1 of alpha 1 and alpha 2 equal to JH alpha 1, alpha 2 minus JAE alpha 1, alpha 2. I'll call G2 alpha 1, alpha 2, JH alpha 1, alpha 2 minus J sub AP alpha 1, alpha 2. And then G3 is this going to be J, the regular aero-assist minus the parabolic aero-assist, like so. And we want to understand, when are these 0, or basically when is it positive, when is it negative, to figure out what the different zones of these guys are. Once we understand their optimality with respect to each other, then we can go back and compare their optimality with respect to the parabolic transfer. Yeah. So one of these is relatively easy. So we'll just take a look at that, and we'll have some indication about how the other two guys turn out. But it turns out that this guy is something that you can do pretty straightforwardly. And one of the reasons is, if you go back and look at the cost functions, both of these guys have the exact same structure for how the cost depends on alpha 2, or that final radius. So if we take the difference of these two guys, it's going to be independent of alpha 2. And that's what makes it a bit easier. So G3 turns out to be 1 over root alpha 1 minus root 2 alpha 1, 1 plus alpha 1, minus root 2 over root alpha 1 plus, because it's minus 1 over root alpha 1. Okay? Do the math. Simplify. This guy is equal to square root of 2 over alpha 1 times root 2 minus 1 over root 1 plus alpha 1. So first of all, this guy is independent of alpha 2, which means whether you use this elliptic orbit or the parabolic orbit to do your aero-assist, which one is optimal only depends on your starting radius. It doesn't depend on where you want to go. So let's set this equal to 0. Actually, to make it a little bit easier, we should just make it greater than or equal to 0, because then it'll give us the answer that we want. So do some evaluation, basically some algebra, and what you end up with is 1 plus alpha 1 greater than or equal to root 2 plus 1, which you can further simplify to alpha 1 greater than or equal to 2 plus 2 root 2, which is approximately equal to 4.83 dot, dot, dot. You get a different number. You get a different radius. And what this really means is whenever alpha 1 is greater than or equal to 2 root 2 plus 1, the parabolic aero-assist is optimal over the elliptic, or J A sub E P, or sorry, J A sub P is less than or equal to J A E. Now, obviously, it doesn't mean that you would actually carry out this parabolic transfer, but what it gives you an indication is that if your initial radius above this planet is much larger than 4.8 something or other, you may actually want to explore going out and then coming back in instead of just jumping down into a lower radius. Because it does indicate that, especially if you're much larger than this value, that you probably will be able to find a transitional L, if you will, that will actually save you propellant over this other approach. What does this stuff really cost you? You may have imagined already. It really costs you time, because all of these options actually take longer than the traditional Hohmann transfer. If we actually go back to this optimality chart that I started, it's still isn't good enough. We can arbitrarily divide these guys by radius, so this becomes alpha 1, alpha 2. The meaning has changed somewhat, but you certainly know that you never want your alpha 1 or your alpha 2 to be less than 1. So that means that you would be in the atmosphere. So it actually just gives this some nice physical meaning or perspective. So what this means is, independent of alpha 2, whenever alpha 1 is larger than 4.8 ... if you actually want to transfer from alpha 1 to alpha 2, this aero-assist option will be optimal over the parabolic option. So we still have no idea how that relates to the Hohmann transfer option. This is just a comparison between parabolic and elliptic aero-assist options. So we can't get too excited yet. Okay. So next, let's look at G2 of alpha 1, alpha 2, and I believe, yeah, this is JH minus J aero-assist parabolic option. This function, 2 over alpha 1, root 2 minus 1, minus 2 alpha 2, alpha 1 plus alpha 2, plus root alpha 1 over alpha 2, alpha 1 plus alpha 2, minus 2 over root alpha 2, 2 over alpha 2, 1 plus alpha 2. Okay. And any nicety that we may have had has pretty much disappeared. You can start plotting this, but with these comparisons, you have to do a lot of plots at a lot of different values in order to sort of tease out what's going on. What's often helpful is actually to take some limiting values and try to understand the extremes and see if there's something interesting in between the extremes. And that's sort of what we do here. So let's look at some limits. First of all, if alpha 1 goes off to infinity, what what do we get? This guy disappears, this guy disappears, this guy exists, and then these guys exist. So if you do limit infinity of G2, what you get is something that's only a function of alpha 2. 2 over alpha 2 minus 2 over root alpha 2, root 2, alpha 2, alpha 2. And here we can be interested in when this is equal to 0. The solution to this guy, well, it actually turns out to be alpha 2 equals 2 root 2 plus 1, 4.83, which is the same limit we found before regarding when the aero-assist parabolic is optimal over the aero-assist elliptic. So what does this tell us? Well, it gives us a very limited bit of information, but it gives us something. If alpha 2 is greater than or equal to 4.83 and alpha 1 is extremely large, then the hyperbolic or the Hohmann transfer cost is actually less than this parabolic cost. We can take the other extreme and make alpha 1 equal to alpha 2, and we'll just call these guys alpha. And we get G2 of alpha alpha is equal to root 2 over alpha, 1 over root 1 plus alpha minus 1. And here what we can show pretty easily is that this is less than 0 for all alpha greater than or equal to 1. And furthermore, it's important to know that this is a definite inequality. And here it means that there always exists a zone close to alpha 1 equals alpha 2 where the Hohmann transfer is always optimal. Doesn't say how large this zone is, but the fact that this is a definite inequality means that there's room for alpha 1 to become larger and this guy to still be less than 0. And in fact, if we go back there to this guy, first of all, in terms of the aero-assist, we can never have alpha 2 greater than alpha 1. So this is all off limits. But it does mean that somewhere in the vicinity of this alpha 1 equals alpha 2, there is going to still be a zone where JH is less than the aero-assist value, at least the parabolic value. And then we know once we're outside of this 4.8 whatever radius, the aero-assist value is optimal over the aero-assist elliptic, so that this guy is definitely Hohmann transfer territory. And we can do a couple more things. And here, we almost have to just start playing around to understand what's going on. And if we just sort of arbitrarily let alpha 2 equals 1, you can show that G22 is definitely less than 0. I'm sorry. What we want to do is for alpha 2 equals 1, because this is the lowest value of alpha 2 that we could have, so it might be of interest. Find G2 of alpha 1 and 1 such that this guy is less than or equal to 0, because that'll then delineate where Hohmann is optimal over aero-assist. And in fact, you can find that J1, 1 is definitely equal less than 0. J2 of 2, 1. If you actually go through the math, this is equal to like minus 8.4 dot 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 10 to the minus 3, almost 0. And so you can actually do a little trick and say alpha 1 is equal to 2 plus epsilon. Do an expansion because we know we're close to 0, so epsilon should be small. And we can actually find, to make this guy equal to 0, to find this transition point, epsilon is equal to 0.0365. And we come up with the following result. If alpha 1 is greater than or equal to 2.065 dot, 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 and alpha 2 is equal to 1, this parabolic cost is less than the Hohmann transfer cost. And while this isn't a definite result, if we go back to the optimality chart, it does tell us that actually starting at this 2 value, that actually the aero-assist parabolic starts to become optimal over the Hohmann. This all gets confusing because this is also the realm where the aero-assist elliptic transfer should be optimal over the parabolic. So that really implies that you might actually be able to push this whole guy further to the left. So to end up with, you finally want to consider G1, which is JH minus J of the elliptic aero-assist option. And what we can show, I'm not going to go through the math, but if we consider, first of all, this limiting case of alpha 1, alpha 2 equals 1, that this whole inequality simplifies, or this whole function simplifies to 2 alpha 1 over 1 plus alpha 1 minus 1. If we want to find when this is less than or equal to 0, it turns out, that'll be where the Hohmann is optimal. It turns out that this is less than or equal to 0 for alpha less than or equal to 1. What does that mean? Well, we know that alpha 1 has to be greater than 1, and it means along that line of alpha 2 equals 1 that the aero-assist option is always less costly than the Hohmann transfer option. So let me just sketch the little chart here instead of going back. the equality line. This is the uninteresting line, region alpha 2, alpha 1. It means along this axis here, the aero-assist options, either E or P, are always less than the Hohmann transfer options. Because once we get beyond this 4 value, the parabolic option is always less than the elliptic option. And here we see that the elliptic option is always less than the Hohmann option. That holds along that line. What we can actually do is try to find if this guy sort of extends from the origin even. And what you can do is actually expand G1 about the origin 1, 1 using alpha 1 is equal to 1 plus some parameter A epsilon, and alpha 2 is equal to 1 plus epsilon, and then solve this equation for this slope parameter A. And that's actually going to give us some information about the slope of this line as it comes out of the origin of this plot. You go through the math, you find that A is equal to 3. So what that really means is that for alpha 2 less than or equal to 1/3 of alpha 1, the aero-assist is going to be optimal over the Hohmann transfer. So that just tells us right in this origin, but it tells us that the slope of this guy is 1/3. And then what we don't know is how does this aero-assist option dominate over the Hohmann option as you go to larger values. You can do the math. You can sort of, by using contour plots and other comparison methods, actually evaluate how all these regions compare to each other in terms of the Hohmann transfer and in terms of the parabolic versus elliptic aero-assist option. But after you do all that, you still have to finally compare it with the, I'll call it J sub BP, for the biparabolic transfer option. And so here we would actually form what we call G4, 1 alpha 2, and we have stated the parabolic aero-assist option before. The biparabolic transfer actually turns out to be root 2 minus 1 over root alpha 1 plus root 2 minus 1 over root alpha 2 with our different normalization. We also realize that here the transfer over this guy relative to the Hohmann transfer occurred at a ratio of like 11 point something or other. So we don't really have to compare the optimality of the biparabolic transfer with the elliptic aero-assist. We only need to compare it with respect to the parabolic aero-assist option. So we formed this G4 function, and luckily this guy turns out to be pretty easy. It's just the difference of, sorry, I didn't say that. aero-assist parabolic minus biparabolic, and it's root 2 over alpha 2 times root 2 minus 1 over root 1 plus alpha 2. And in fact, it's independent of alpha 1, which makes sense since both of them start off with boosting yourself up to escape speed. We want to know when is this guy less than or equal to 0, because it tells us when this guy is cheaper than the biparabolic transfer. And if you actually go through the math, we find again that alpha 2, that this guy is less than or equal to 0 when alpha 2 is 0. Yeah, when alpha 2 is less than or equal to 4.83. So it turns out that this guy is optimal over the biparabolic transfer for all alpha 1 if alpha 2 is less than or equal to 4.83. So again, you can take that to your chart and show it graphically. And I'm not going to do that because it starts to get a little bit too messy. Ultimately, I am going to sketch this out. We come up with an optimality chart for the classic Hohmann transfer. Oh, and I'm over time, aren't I? Sorry. So I'll give that to you next. Sorry, I lost track of time. But yeah, then we'll finish this. Then we'll talk about the practicality of some of these guys. Then we'll go into a little detail on plane change transfers, and that'll sort of end this introduction part of the course. And then we'll get into the slightly more hardcore stuff, parametric optimization, and then functional optimization for optimal control. So we're almost done with this introductory material on just simple two-body transfers.